Okay. First, I will give you an introduction on what is the model testbed. MoT or model testbed is the mathematical software design. This is the equation-based modeling and simulation tools and allow user to perform the simulation of the process without having to write any source code. The MoT can be opened from the project and here, and they can open on the iCAD like this. Okay, and the workflow of MoTs are 7 steps that are modeling objective system informations, followed by single scale model construction, multi-scale scenario constructions, model identification and discriminations, model evaluation and validations, simulation and optimizations. And this is the interface of the MoT. There are 2 parts, which are the mode selection and the working area here. In the MoT mode, there are 3 available modes, which are definitions, solutions, and the analysis mode. In the definition modes, this is the place for the modeling objective, system information and documentations, model construction or model creations, model analysis where the variable classifications are here, and the testbed environment. And for the solution modes, there are 3 functions here, which are model solutions, optimizer, and report. And the last one is analysis mode. The option on calculation the result will be available, such as sensitivities, identifiabilities, analysis, and Monte Carlo. And to explain each MoT mode, we will bring 6 example cases for showing the different problem on MoT functions. The example 1 is the demonstration of the model creation problem, which is highlighted through the reactor model. The problem definition is from Fogler books, that is the model combination of ordinary differential equation plus algebraic equations. The problem is semi-batch reactor having the heat exchanger inside, which had a series reaction as presented here, and the catalyzed by H2SO4, and all reactions are first order, and the reaction rate is independent of the catalyst concentrations. In the reactor model, there are 2 parts of the equations that are differential equations and algebraic equations. For the differential equations, mole balance and energy balance are presented. And for the algebraic equations, the kinetic constant in Arrhenius type and the rate of reaction were included. So the summarizing that the process model is given by 4 ordinary equations and 5 algebraic equations as shown as in the latest box here. And then all the variables were transferred to MoT variable as presented here, and the model of reactor will be applied in the problem solutions. So next, Professor Rafiqul will demonstrate you on the solution step of the reactor model through the MoT software.
Okay, so thank you. I will share my screen. So first, can you see the modeling framework?
Yes.
Okay, so during my presentation, I talked about a model template that can help us to generate different forms of model. That is the model template. ModDef is the one that generates models. We can describe our system and it will write the equations for us. MoT model library is a library of models that we have collected. And what I'm going to show you is MoT today. There's no time for ModTem and ModDev, although they would be very interesting. But if you take a 1-week course on modeling, then I show those things. But then we go to MoT. And okay, I will just use this. Because it will take time to go through all these steps, I will show you those steps afterwards through a report of the model. But I will just enter MoT. And if I enter MoT, this is what you will see. And it's a blank space here. And we have the menu kind of explorer tree kind of thing here. So the first thing we want to do is to import a model into MoT. So we need an import feature, and the import feature is very simple. If we have saved the equations as a text file, so I've saved the model equations as a text file, something easy to do. Either you save the Word document as a text document, or you scan and put the equations in that text file. So I've just created a Word document. And the equations and text are given here. So you can see here that all the parameter values are explicitly given as an equation. And that has some importance that we will discuss afterwards. But you can see that all the equations are here. So there are different ways to import a model. It's possible to import XML files, text files, and even other forms of import is possible. What I will do is just, I will copy this. Control C, and then I will go into MoT. And where there is model construction, it says view original model. It's blank here. So I will just paste it. Okay, that is as simple as importing the equations. So once I've done this, let me just explain also a little bit this the language issues. If we have this mark on the first column, then it means that these are comments. So we have comments, and then we have equations. And also with respect to equations, if we have the variable on the left-hand side and numbers or variables on the right-hand side, they are taken as explicit algebraic equations. So this is, for example, an explicit algebraic equation. So we can see that all the equations are actually explicit. Whenever there is a variable on the left-hand side, which starts with small d, they are indicating an ordinary differential equation. So these are the syntax. So ordinary differential equations are highlighted through the small d. So that's the energy balance equation. That is the three mass balance equation. All the other equations on the left-hand side is a variable, on the right-hand side are variables. If all the variables on the right-hand side are known, then it is an explicit algebraic equations. The system will automatically know it. So once we have put these equations, then we need to go here and say accept those equations or accept the changes. So it will then identify the variables, everything. I will just say accept. Then it could be that we have compounds for which we need parameters like critical temperature, pressure, or enthalpy correlations. If we have those kind of compounds, then we need to tell so that it can extract those equations from the library. In this case, all the data are given, are self-contained. So we say compounds are not used. Compounds are used, but we don't need the data for the compounds. So we say yes. So the first thing it does is it converts our text equations into a form that the computer can work with. And here the reverse Polish notation is a form to do that. So now we have a form of the equations that the computer can understand. And that is the view translated model. So computer has already done that. So the next step is to tell the computer or the system about the variables, what kind of variables they are, what kind of equations they are, and we have to satisfy the degrees of freedom. So we go to classify variables. And in this problem, actually, since all the equations are already, parameter values are already given as equations, so we do not have any other parameters. The only ones that we have are T, CA, CB, CC. These are not really parameters, so we need to tell the system that this is a dependent variable, that is the dTd for the differential equation. Similarly, CA is a differential equation, CB is a differential equation, CC is a differential equation. T is an independent variable, it doesn't matter here. So we have given this. So now the computer already knows that we have 4 differential equations, and the differential equations, variables for the differential equations are these. And there is no other known variable because they are already explicitly put. There are no unknown variables because we do not have any implicit algebraic equations, and the only parameter is this. What we can also see here is a color code where if there is a implicit algebraic equation, the variable will be shown as red. If there are known variables, will be shown as green, parameter blue, explicit variables yellow, and light blue is the differential equations. So we close this, and we can see the incidence matrix. On the left-hand side, the rows are the equations and the columns are the variables. So what it does also, it makes a lower tridiagonal form for the equations. So if it is lower tridiagonal, then no iterations are required because the algebraic equations are explicit. In principle, all the algebraic equations can be inserted into the differential equation, and we will have only the differential equations. But we are not ready for the solution because we have to say how to relate the dy dt to t. So, sorry, dy dt to y. So we come here and then we say that t is related to, the variable t is related to dt, the variable ca is related to dca, cb, and cc. So now the system knows exactly the 4 differential equations, the variables relating the 4 differential equations, and all the other differential equations on the right-hand side are explicit algebraic equations. They can be calculated from the known initial values. So if we go back to the view translated model, we can see we can calculate the right-hand side of this differential equation if all of these are known. And since we are organizing it as a lower tridiagonal form, they will be known when they come here. So then the final thing that needs to be given is the set variable value. So again, let's go to this, let's look at here. So you can see that CA0, V0, UA, these are all actually parameters, but we have given them already the value as was given in the model in Fogler's book. So we have not changed that. But if we did not give this TA, then it would be as a parameter and we would have to give the value here. So we go to set variable value. Then because we have it has identified that this is the initial value differential dynamic problem. So we need to give initial values for temperature and the compositions. So 298 is what is in the book. And concentration of A is the reactant. So it starts with 1 B and C are the products, it starts with 0. There's nothing else to specify. The time by default is 0. So now we have the equations, we have given all the variables that needs to be given. We need to set up the solver and we need to say what to plot. So we go to solution. We go to variable chart. We say, show the variables. We want to see T. We want to see CA, CB, CC. And we can also have other variables, but let's say we want to do this. We save it. And now basically we are ready to solve. There are two options to solve. One is what we call step solve. And what this means is that it's just a calculator. You can just click and one by one, it will just show the calculated values. So whatever is on the right-hand side, it will calculate. So up to now, it's just the actual values. But when we go to equation 21, you will see some calculated value. Okay, so based on all the values in here, it calculates K1A. And this is a nice feature because before we actually set up the solver, it is a good idea to check whether there is some strange value somewhere. If there is, maybe there is some problem with the equation or the values. So it's just a calculator. And then once we have checked this, then we go to the solver. And there are different ways to go to the solver. We can go to the solver here, but the easier way is here. We click there. And we have the solvers for algebraic equations, for DAE or DE solver, and we have optimizer. So this is a DAE solver. So we have the BDF and RK method, fifth order. So by default, we can take the forward integration and we can change the time scale to 0.02. And we can say what should be the end time, 1.5. Then it automatically calculates that if the time scale is 0.02 and we want to end, it will need 357 integration steps. And these are not fixed step size, it is variable step size. So we have defined all of these. Now we are ready to run the problem. So we click on solve. We just say that the file name is testweb1. So it has actually finished calculating. I need to, I increased the size, but now I can see that I have a problem to access the plots. Is it this one? No. Just a minute, I need to do something to access the plots. Don't close it. Oh, here it is. Now the size of the screen will be, text will be a little bit smaller, but you would be able to see this other things. Okay, so I will run the problem again. Everything is set. So run. And then it will create the plots. This is how the temperature will be. This is how the concentration is for A, for B, for C. Now, you would think that A is the reactant, and how is the reactant concentration increasing? Is that correct? It is actually correct because Ca is not mole fraction, is moles per liter. And because the concentration is changing, the density is changing. So because of that, the Ca in moles per liter is changing and increasing and then decreasing and then comes to a steady state. Okay, so we can close this now, and then we can close this. We can go to the run again. And as I said, analysis of the model is very important. So we have an option here also to say that generate eigenvalues. So if we click there and we solve, so we close this and we go to the solution result. There is the eigenvalue report and we can see the eigenvalues. The eigenvalues are negative, the maximum and minimum, which indicates that this is a stable solution. So very useful information is also there. We can also set up multiple runs and things like that. So that was just the small part of importing a model, then setting up the calculation strategy, providing the input data. The solvers are already connected, solve, and then see the output. And also with the output, I have to generate the output again. So it is possible to magnify if I want to do that. So I can magnify, or I can go back to the original. I can combine plots. So add all. I'll remove the temperature because it's a different scale. And then in one plot, the three will be shown. And I can save the points, generated points, and I can use other means of drawing the graphs and things like that. It will be saved as a ASCII file that can be opened in Excel. Okay, so this is the end of the first problem. And I will show all the different features when they are available. Okay, so I will close it. I will close it. If I save everything, then this problem is saved. If I can discard it, then nothing will be saved. It doesn't matter. I will just close it here. And I will close the Word document. And now I will stop the sharing, and Orakotch can explain the second problem.
Okay, turn back to me again. Okay, the example 2 is the modeling of PDAEs, or partial differential algebraic equations. PDAEs will be presented to the case of the transients diffusion through the first order reaction in the catalyst lab. And the equations and all things are presented here. The model is the partial equation plus boundary conditions given by algebraic equations. So this is the PDAE system. Then Professor Rafiq will show you the modeling step from the model import to the porting of the results and checking the result. Okay, I will stop here.
Okay. Okay, so I will share the screen. And I will go, this time I will not go to MoT. What I will do is I will directly open a saved file that is called Wildson collocation. So exactly the problem that Orakotch presented, I will open this file so we can skip some of the steps. This is a very simple problem. And I will first show you how the original model looks like. So that's the second order partial differential equation that Orakotch showed. And then the initial conditions, the boundary conditions. So the syntax, if an equation on the left-hand side starts with partial, the system knows that it's a partial differential equation, and double X means second order, single X would be first order, X means X direction, and T is the dynamic. So it's a dynamic model distributed in one direction, X, and then there is a algebraic part. So this is our partial differential equations. So if we want to solve this, the method for solving partial differential equation is to use collocation. And by collocation, we discretize the partial differential equations into algebraic equations or differential equations. So in this case, the problem is already discretized. If we go to the view model, it's only showing the boundary condition, the initial condition, and the partial. And if we click in here, we see that there are 3 collocation points and there are 3 differential equations. There's only one here, but there are 3 collocation points. And for 3 collocation points, there are 3 differential equations. So the system automatically does the discretization, and I will show you later how it works. So we have now already the translated model. We have to do the same thing that we did before, classify variables. These are already classified. Now y and lambda, these are parameters, and y1, y2, y3, these are the differential variables. So these are the differential equations, and these are the explicit algebraic equations. So then we go to set variable value. We need to give initial condition. So this is 0 here, all of them. And here is 0 and 1 for lambda. So everything is set. We do not need to give anything for the explicit and the dependent prime. It is going to calculate. Dependent prime is the right-hand side of the differential equations. So we directly go to the solver. This is also a dynamic model. So the solver has already set up this. We are just using the default, and we can click on solve. So now we see this is y1, y2, y3. If we combine the plot, you see the distribution with respect to space. Okay, so this one starts first, then after some time this one starts, and then after some time this one starts, and in different color. So whatever other commercial solvers like this can do, like MATLAB and others, we can do. We don't have the very nice plots, but we have all the data. And again, you can save this data and plot whichever way you want. So this was with the orthogonal collocation. And in order to see how the collocation is done, I will go to the original model. And if I just make a blank space and ask the system to accept the change, the system will accept the change. And then it will notice that this is a partial differential equation. It will ask if we want orthogonal collocation or method of lines. So if we say orthogonal collocation, then we give the collocation points. We give information about the interpolation points, coordinate system, and the value of alpha, beta, and then it is ready to do. Okay, so once we give that, the system will automatically do the collocation for us. And compounds are not used here. So we go back to this. So I will close this one here. And I will show you the method of lines also. I will show you all the model reports later, but let's go to the method of lines. So the problem is still the same, but now the translated model, if I click there, method of line has used 9 discretization points. So now we have 9 differential equations to solve. Everything else is the same as before. Classify variable. It's just a bigger set of equations. Set variable value is a bigger set of variable values that we need to give. And then we run it. And now we can collect all of them. And we see the nice distributed values. So this is the last one. This is the first one. They may match with the collocation and one in the middle. So we can solve, there can be a dynamic variable and 2 space. We cannot solve at this moment. We have not put the discretization for 3 dimension. We have put the discretization for 1 dimension, 2 dimension. So 2D problems with dynamics, 1D problem with dynamic, in the sense that they will be discretized in one direction, can be solved. And these are all problems, we call this problem Wildson because the paper by Wildson and Stewart, I think in 1967, they specifically proposed orthogonal collocation to solve this problem. So we match exactly their solution. So then Orakotch will take over and introduce problem 3.
Okay. The example 3 is related to the problem for the process optimizations. The simultaneous process simulation and optimization of William Otto Pan will be demonstrated. The problem here is from Systematic Method of the Chemical Process Design textbook by Baker, Gossman, and Westerberg. Williams Otto Pans was include the CSTR, heat exchanger, decanter, and distillation as presented in this figure. And the objective function is defined as the return on the investment and is given in the term of net sale minus fixed charge, raw material, utilities, waste disposal costs. And next, Professor Rafiq will explain you on the problem setup and the solution step of this example.
Okay, so again, I will share my screen by going to my files. So again, I will open the Williams Otto plant problem. This has more equations, but let's go up and see the equations first. So now there are many new things in here. So you see 0 on the left-hand side. What does it mean? That means that these set of equations are implicit. Every equation has more than one unknown variable. So we need to indicate that these are implicit algebraic equations. But on the other hand, this is an explicit algebraic equation. These are explicit algebraic equations. And then there are implicit algebraic equations. So it's a system of equations with implicit and explicit, because this is a process simulator. Basically, all these equations are coming from a process simulator. So solving all of these equations, we will have all the variables that we need to calculate the return of investment. So what we need to do then is to tell the solver, solve the algebraic equations with an algebraic solver and do the optimization with an optimizer. So we need to combine two solvers, the algebraic equation solver for the algebraic equation, the simulator, and the optimizer to do the optimization. But then we also need to say, what is the objective function? Which are the design variables? Which are the constraints? So I will show you how this is done. So again, we go to the classify variable. Now you can see a lot of red color. And the red color is because these are implicit algebraic equations and the variables related to them. The dark blue are the parameters. If we don't want to see the parameters because they are already specified, we can take them off. Then we just see the explicit algebraic equations and the implicit algebraic equations. There's no difference. Sorry?
It shows only the file in the document, not in the MoT one. You can reshare it again.
Oh, okay.
Mm-hmm.
Oh, share screen. Can you see the screen now?
Yes,
with the
in
colors?
The MoT. Yes.
Yeah, okay. So what I did was I took the color out. If I put the color again, then you will see the blue color for the parameters. And I can take the blue colors out, so the parameters will not be shown. And then we can see how it will look like with respect to solving the whole set of equations. We can zoom out, then it becomes smaller. So there are subsets of implicit algebraic equations and explicit algebraic equations. And this incidence matrix determines the calculation order for the equations. Okay. And then we go to the set variable value. Unknown variables we don't need to worry about. They will be recalculated. We do not have any dependent or dependent prime. We do not worry about explicit, they will be calculated. We only worry about the parameters. These would be used as initial estimates, and there are no other variables. So once these are given, then we go to the optimizer, we go to the solution, and we go to this part which says optimizer. There is no experimental data to give, so we close that. It will be for other, but we have design variables. So we click there and we say that FA, V, FB, T, and eta, they are active design variables. So the optimizer will know that it has to change these variables in order to do the optimization. There are constraints. These are all the algebraic equations. They have to be satisfied. And then we have to say what is the objective function. Then we are saying that it needs to minimize ROI. So now we have said what are the design variables, what are the objective function. We are ready to run. So we go to the run. We say that solve the algebraic equations with Weckstein and optimizer with this. And then we click on solve. So what will happen is that it will first solve the algebraic equations, then do an iteration in the optimizer, and like that it will proceed. So as the red curve proceeds, these are the iterations in the optimizer. Okay, so there is inner loop for the algebraic equation solver, outer loop for the optimizer. It needed about 10 iterations to come to this value. And if you compare this result with GAM solver or Bigler's values, actually our objective function is a little bit smaller. So that is a process optimization. Okay, so next, problems 4 and 5, we will show parameter regression. So we are also going to do optimization, but now we will take experimental data and we will match the experimental data and we will change the parameters. So that's another kind of optimization. So we close this. We close this. Okay.
Okay. Continue to the next example. The example 4 is the demonstration of the regressions model parameters for the kinetic model. The model are here from the catalytic cracking of gas oil to gasoline and other side product, which the reaction are shown here. The model is given as the dz1 and dz2 is equations, and the objective is to estimate the model parameter with the measured data available. For the demonstration, Professor Rafiq will provide you the explanation of each solution step. Okay.
Okay, so I will again open. And okay, so do you see my screen or I have to share my screen?
I can see in the MoT file document.
Do you see the MoT now?
Yes.
Okay, so let me explain a little bit more. So we have two reactions, A going to Q and Q going to S. And A to Q is a forward and backward reaction, and Q going to S is a forward reaction. So Z1 is A, Z2 is Q. People have measured the data for Z1, for A and Q as a function of time. So we have the data for A and Q, which is Z1 and Z2, and then we want to find what are the optimal values for K1, K3, and K2. That matches the data best. So the translated model again is very simple. It's just two differential equations, classify variables, all of these. K1, K2, K3 are parameters, but there are initial values for these. And we relate the differential equations, Z1 to dZ1, Z2 to dZ2. We go to the set variable value. Initially, Z1 is 1, Z2 is 0. And these are the initial values of the three parameters, 10, 1, and 15. We don't need to worry about that. It will be calculated. So, but now we need to put the experimental data because we are going to fit data. So we go to experimental measurements, and there is two sets of data. set 1 and set 2. Again, ignore current value and difference. With as a function of time, measured Z1 is there, and in the next one, measured Z2 is there. So we have two sets of values. Because it's a differential equation, there's no experimental condition. The experimental condition is at different time. Different Z1 and Z2 has been measured. Then we go to design variable. And now you can see that the design variables are the 3 parameters. They are active. And then there's no constraints in here also. Object function pairing. We don't give an objective function. We already have predefined objective function for minimizing the least squares. So we take this one as the objective function to minimize. So we say, okay, here, and we are basically ready to run the optimization. So now what will happen compared to before is that we have differential equation. So inner loop will do the integration, outer loop will do the optimization. So we can go here, inner loop, this is the integration, outer loop, this is the optimization, okay? So we click on solve. So this is doing the dynamic simulation. And then as this curve moves, this is the outer loop optimization iterations. And while this is doing, I can explain a little bit more. What I will show you also is that this, so in the inner loop, we are solving for the differential equation. So at every iteration of the optimizer, it needs to solve the differential equations from time 0 to time end for which the data is available. Then it checks the objective function, and then based on this objective function, it looks at the parameters. So we can also look at the parameters. So obviously, when we have reached a solution, not only the objective functions should satisfy the optimality criteria, the parameters should also not change compared to previous iterations. So I know that it will take about 51 iterations. So you will see that as we are going towards 51, the parameters will come to a steady value also. So this is, I would say, brute force dynamic optimization, because we are doing the dynamic simulation and then we are doing the optimization. One thing we could have done is using orthogonal collocation, convert the differential equations into algebraic equations, and then solve algebraic optimization problem. And you will see that Bigler has a GAMS example on that. So that also we can do. We can convert the differential equations into algebraic equations through collocation, and then set up a algebraic equation based optimization. But since this is very fast, we can do all these together. So you can see that it is in almost steady state, steady, and steady. And again, this problem has been reported in the literature. Our objective function value is smaller than the objective function value is also given here, is smaller than the reported one. So we can actually find better solution. So again, if we combine, these are how the 3 parameters look like. I will show you the sensitivity analysis of the parameters in the next regression problem. So now we can also look at the optimization report. So then it gives the statistics for the optimization. It gives the confidence interval. It calculates these. Oh, sorry, we can go from the top. Optimization report. These are the 3 parameters that needs to be optimized. The problem setup information, Then the experimental data, calculated value, sum of squares difference for set 1, set 2. Then the mean values, sum of squares, all kinds of variance, standard deviation, statistics with respect to correlation coefficient, coefficient of correlation or R square, adjusted R square, all kinds of statistics that you will find in statistic books, ANOVA statistics, these are all given. So if one wants to do model discrimination, these variables, these values are quite important to see which one gives the best in terms of fitting the data. So all these are given. Okay, so Orakotch, you can do the next one.
Okay. The example 5 is the regressions model for the parameter fittings of the NRTL model. And the equations of the NRTL and VLE calculation is given on the right-hand side here. Tau 1 and tau 2 that's used in the equations for tau 1, 2 and tau 2, 1 are the NRT model parameters that are to be estimated through the regressions using the measured data of the VLE. At each data points, X and P are given and T and Y are calculated. So it involves solution of implicity set of algebraic equations in the inner loop and the optimization in the outer loop. For the solution step again, Professor Rafiq will show you the explanation on it. Okay.
So I will share the screen and I will go there first. And I will show you afterwards all the different models we have, but I will take a binary mixture to make it fast. But we also have ternary mixture and multi-component mixture, and we can do multiple parameter estimations in the same go. So if we take a ternary mixture, for example, methanol, water, ethanol, there will be 3 binary pairs, and then we will add the 3 binary pair data, and it will fit 3 binary pairs. If I give only a binary mixture, then it's only 1 binary pair. So this one takes a longer time. So I will just use the binary mixture. So we open it. And I will need to share the screen again. Do you see the MoT screen now?
Yes.
Okay, so now it's very interesting problem. If you are interested in thermodynamics and VLE calculation, so it's a binary mixture. So what it is doing is that we have data for PTXY, pressure is fixed for different compositions in the liquid. It has measured data of temperature and vapor composition. So we then set up the problem that we will specify the X, that is the measured X. We will specify the pressure. We will calculate the temperature, which will be the bubble point, and we will calculate the bubble point composition. So to do that, first, we set up the calculation of the activity coefficient with the NRTL model. So this is the NRTL model for a binary mixture. And then what you see here, par 1 and par 2 are the 2 parameters, interaction parameter between methanol water and water methanol. And then we get the activity coefficients, gamma 1 and gamma 2. But that is not enough. We also need the vapor pressures. So here is the vapor pressure model, and A1, B1, and C1 have been fitted previously in a previous step. So we have the vapor pressure fitted that we put directly here. And then this is the equilibrium condition. That is the isofugacity criteria. Y1 is equal to X1 times P saturated, gamma divided by P. And then we calculate Y1 and Y2. And then the summation of Y1 and Y2 minus 1 has to be 0. So this is an implicit algebraic equation. And we have to do that for every data point. So that means the optimizer will have to set the parameter values, par 1 and par 2. Then knowing the parameter values, it will calculate the T and Y1, Y2 for all the data points. Then it will calculate the objective function, and based on that, it will get new parameter values. So again, we look at the translated model, which looks very compact. Then we go to the classify variables. So now you can see all the different colors. We will keep the red because this is the implicit algebraic equation. We take the known variables out. What is the known variable? The known variable is X1, R, and P. That is the process conditions. So we take them out. So the green is out. We take the dark blue out. These are the parameters. A1, A2, A3, B1, B2, B3, and the par 1, par 2. So now it's nice lower tridiagonal, except for the red. So how the calculation will be done? It will first do this calculation, then it will assume T, then it will calculate tau 1 and tau 2, and then it will do all these calculations. And after doing all these calculations, it will check if the residual is 0 or less than error. If not, it will guess temperature and restart. So that's the calculation order. And the system automatically finds that and sets it up. We do not have any differential equations to worry about. We can look at the set variable value. As I said, these are not needed. The known variables are needed. R is the universal gas constant, P is the constant pressure, and these are the parameters. I will set this parameter to -10 and +10 just to make it do some work. So these two parameters need to be fitted. So now we have set the variable values. Then we need to go to the solution. We need to go to the experimental measurement. And then you can see that, again, just ignore the current value and difference. We have measured Y1, this is this, and we have measured temperature, this is those. Okay, so we have two sets of measured data. But now in this problem, for measurement of Y and temperature, there is also measured X and P. So we say that the X and P were the experimental conditions. And if we click on X1, we see the data for X1 and we see the data for P. Okay, so there are 20 data points, and each of these, it has to do the bubble point calculation, check the pressure and check the Y and temperature so that it can calculate the objective function. So then we go to the design variables and nothing is chosen. If nothing is chosen here, then it does not do the optimization, it just do the calculation. But we will say this and these are active. So it will do the optimization and find these two optimal values. There are no constraints in here, objective function. We say this is the objective function we want to minimize. And now we go to the solver. So again, we need algebraic solver, is a Newton-Raphson method, and the optimizer is the same as before. So now we do the optimization. It did very fast, I think, or what happened? Let's change the objective function and see what happens. I probably did not select something properly. So now it is doing the optimization, okay? And then, so it needed 5 iterations to come to the objective, to the optimal solution. This is the parameter 1, and this is the parameter 2. Okay, so now we close this. We can update the known variables. Actually, I think there's something probably I did not do properly, so I will close this one. And no, don't, I'm not stopping the sharing of screen. Can you see the MoT screen now?
No.
Okay, so now you should be able to see it.
Yes.
Okay, so let's go to the set variable value. This is this, and the design variable value. This is this. So now the problem is properly set up, and then the experimental measurements are still there. And we go to the objective function. We do this objective function, and we say, okay, and we want to run it. So we have the objective function value. We can see all the results here if we want. All the results, and you can see the residual will be very small. Where is the residual? Here, it's very, very small. So it has satisfied all the calculated values. So now what we will do is we will ask it to update the unknown variables, and it will also update the parameters. So it will do that. We will close it. And then we will set up in the analysis, the sensitivity analysis. I will only show you the local sensitivity, not the global sensitivity, because that will take time. So the local sensitivity, first, I choose which are the sensitivity variable parameters, par1 and par2. I take them. Then what is the response variable? It automatically knows that y1 and y2 t should be the response variable. And we do not need to do multiple calculations. We do perturbation. So what it is going to do, it is going to make plus minus 5, 10, 15 perturbations in each of these parameters, and then it will do the calculations. And once we have given that, then we go to sensitivity analysis. It says if we want to do the sensitivity analysis with optimization or without. With optimization will take time, so we will cancel, and we will just generate one value first. So what we will do here is go back to the design variables, and for the sensitivity analysis, we do not need the optimization, so we take them out and we do just a function evaluation. And if we, by doing the function evaluation, what it does is it has in its record the reference value. So now it has the reference value, we close it. and we go to the sensitivity analysis. So now it is perturbing each variable in plus minus direction, 5%, and then it generates the values, and then we can see when it is finished. So it is also again brute force. Each parameter is perturbed and all the calculations are done. And then after that, we will see how the parameters look like and which is the more sensitive. So now it has finished. And so we can go to the analysis and we can see the results in plot. So this is showing just if this is the reference point, when it reduces the value, the Y1 increases, and when it increases the value, Y1 decreases, and the other one. But it's more interesting to look at it from this point of view, where the difference, the square of the difference is taken. And by doing this, we can see that the green is more sensitive than the red. So that way we know that, and in some cases it could be that the parameter is just on the horizontal, which means that whatever value we give, it will not change our calculation. So we do not need to do parameter estimations for them. So, but the green one is more sensitive. If we want to look at it in terms of results in table, we can look at it in terms of parameter significance. We can see that parameter 2 is more significant than parameter 1 because it's more sensitive. Okay, so that was how, after we have done the optimization, we can do parameter estimation, but this is local parameter estimation. A better one is the global one. Because it will take time, I will not do it, but I will show you where you can see all the results. If you have this software, you can go through the steps of these in our manuals. And as I said again, that if I discard this, and then I will share the screen. And I will open the ternary mixture. So now we have a ternary mixture, and we have 3 sets of parameters that we need to fit, not one set of parameters, not par 1 and par 2. We have 3 pairs of parameters. So this is a bigger problem. The data also has more data. We have methanol, water, methanol, water, ethanol, and then temperature. Okay, so the optimization problem is bigger. Everything will take longer time, but at the end, we will have all the parameters we need. If we put 10 compound system, we will calculate all the binary pairs for the 10 compound system. So that depends on the size of the computer and the storage that is allowed. So what I have shown you up to now are parameter estimation, both for thermodynamic properties as well as kinetic models. We have done process optimization where it is not, data is not needed, experimental data. We have solved partial differential equation, distributed model. We have solved dynamic equations. We have solved DAE systems. In the next example, Orakotch will show a big problem that after solving that problem, let's say creating a model, you can create an Excel macro where you can create a simulator based on those model objects. So all of this without having to write any model equations. So finally, what I will show is where you can find all the information. Can you see my screen with the?
Yes.
Okay, so if you go to work and then examples and MoT and new features, so then you can see that there are lots of different examples and more is screening. The model for that is there. If we go to library, static units, different kinds of separation problems. If we go to MoT functions, we have thermodynamic functions. I think we have new features. And thermo models. So you can see CPA, equation of state, electrolyte, uniquac, NRTL electrolyte, NRTL binary, NRTL ternary, PC SAFT, UNIFAC, Wildson, and there's a lot more. I'm not showing all of it. So these are all the models. If we go to docs, manuals, then there is the manual, new features 1, new features 2, which will tell you step by step how to do Morris screening and all other options. Okay, so with that, I will stop here and let Orakotch show the last example.
Okay, another options for the people who are not familiar with the modeling in MoT, we can use the external tool such as Excel, MATLAB, and so on after creation the MoT model objects. So in this demonstration, the comms macro Excel will be illustrated with the example case of the short path evaporators. The short path evaporator is a safe method for separation and purification of substance. The cylindrical body is surrounded by cylinder. One of them acts as the evaporation surface and other as the condensation surface. The liquid material to be distilled is fed to the evaporator wall, and evaporations and the condensation surface are kept at constant temperatures, TW1 and TW2 respectively. And due to the low pressure inside the separators, a falling film is formed and the concentration or temperature profile of the most volatile compound decrease with the axial and radial directions. For the modeling, this issue and hypothesis will be used, and there are 5 types involved equations that are momentum balance, mass balance, energy balance, rate of evaporations, and film thickness. For the momentum balance, the velocity profile of the falling film are presented in equations 1 with these boundary conditions. For the mass balance, the composition profile of each compound are calculated from the diffusion equations. And for the energy balance, temperature profile of falling film are presented here along with the boundary conditions. And lastly, rate of evaporation and film thickness are described in these equations. All the equations will be added into the MoT model for creation of the short path evaporator simulators, and the method applied using centered finite difference is applied in order to solve the evaporators model that involved with the PDAs. And then after the MoT model is created, it can be used from the Excel. So after this, I will demonstrate you on the using Excel with the short path evaporator model. And the demonstration will also highlight in the creation of customized simulated short path evaporator plants and delimine where 2 units are operated in the series. So I will open the testbed file here. This is the short path evaporators which our mentioned model was included here. Next, I will open the macro Excel of MoT interface here. And then When it's open, you will see that there are 3 sheets here: MoT model, dependent variable, and plots. And in the MoT model, there are 2 options here: the load MoT model and manipulate model. I will click load MoT model here and click browse and select the generated short path evaporator here and open. And then all of the variables and value will be shown here. Then I click load model details into the sheet. Then as you can see that all of the variable and parameter will be shown here with the input. And to solve the problem, I have to click this button.
So what it is doing is it is doing a dynamic simulation to generate all the data.
Yes, and then, yes, go. Professor,
no,
go.
you go.
Okay. And then the result of the solving will be shown in this table. And when you go to the dependence variables, the time in this case indicate as the length, and temperature, surface, and all of the 4 of the liquids composition will be shown here. And also, if you want to see the trends of all this this variable, you can go to the plot sheet, and you will see the graph plot between the temperature and length, and liquid composition and length. As you see, that temperature will be increased with the length what increase, or when the liquid falling down. And for the liquid composition fall, the composition one is getting removed when the length is increased. So this is the figure that you can see in overview of the simulations. For this example, you will see that only one short part is operated. And anyway, more than one operator can be operated in the series. So I will close this file and open another smaller case example. This one is the limonene MoT file that we have generated also. I will do the same with the previous one. Open the MoT model interface here, and then load the MoT model, browse the limonene, and open, and click load model detail.
So I can just say one thing in here. The difference between the limonene and the other one is that the other one had 6 compounds, and 1 compound, which is the impurity, like in a pharmaceutical product, you may have a small impurity in very small amount, but the compounds are temperature sensitive, so distillation cannot be used. So short path evaporator is one way to remove very small amounts of material without destabilizing the compounds. That was what was shown. Here, it is just a binary mixture of limonene and water. Water will vaporize out and limonene will concentrate.
Okay, then I have to first solve the first unit by clicking here. And then the result of the first unit will be shown. Then I have to load another unit by clicking at the same way and load the model detail. And you will see that another delimonene will show here. And when you scroll down to the below, you will see another table of the second unit will be shown here. And then I click solve for the second unit. Then also the result of the second unit will be shown here. Okay, you will see that this makes the model use easier for those not familiar with the modeling toolbox environments. So this
So I can just say something more in here. So this is like if an expert user can go into MoT and develop the model and the object, and then users of that model it would be easier for other people to use this Excel with the macro. All they need to do is upload the saved model, and then without any programming or anything, they can create their own customized simulator and they can run these problems.
Okay, that's all for the.
Maybe
Yes.
you can just go directly to MoT and run the MoT just to show the model equations and everything.
Which one? The short part one?
The short, yeah. So go to the, this is a distributed model. The differential equations are with respect to length, and then in one direction in X, the discretization has been made. A method of line has been used to set up the problem. Then you can go to the set variable value. So all the initial values are given in terms of temperature and composition. And then you can go to the run. And this is not dynamic simulation with respect to time. It is dynamic simulation with respect to length. So it is solved as a dynamic simulation problem. Click on the solve. So now you can see the temperature changing and the compositions changing. Okay, so the idea is that first we look at the object and the results, and when they are good, then we create the Excel macro. We already have the Excel macro. All we need to do is load any MoT object, and then it will do exactly what was shown in the Excel file. So we have done the macro for Excel. It can be done for any other software. I know some people have done it for MATLAB, and so other things are also possible. Okay, that is all. I think somebody, maybe I did not share the screen properly, and so maybe you did not see some of the plotting things that I was showing. My apologies, but now you have seen from the last what it is. So there is some question. So Dr. Wang has said, thanks a lot for this excellent seminar series. MoT seems to be a very nice tool for a senior or graduate chem-eng design course. What are the options for us to get it? And how much would it cost? It will be very small amount. We can talk about it. We want to encourage people to use this. So if you have a good plan to use it for educational purposes, we might even give it free. But let's talk about it and see. So anybody else who wants to use it for educational purposes, please contact us. If you want to use it for commercial purposes, then of course we need to make some kind of agreement. But it can solve all kinds of problems. And as you can see, if you have the model, you can take the model by scanning the equations from any text, from a paper. So we can very fast verify a model by scanning the equations from a published paper, put it in here and see if the results that the authors are claiming matched, without us having to write any equations or any programming code. And then we can manipulate the models to do all kinds of things. So I think it's a very powerful tool if people are interested to use it, but it needs some time to get used to it. The difference, I would say, between this and tools like MATLAB or Maple is that here the user needs to know what they're doing. It's not a black box. You just put the equation and then you get the solution. The user needs to know that they are using a dynamic DAE solver, which has integration steps. It calculates the right-hand side to make the new steps, all of those things. It explains the user step by step. But of course, if you're using the Excel macro, then it is like a black box. Okay, are there any other questions? I think we ran out a little bit also in time. So those who are still remaining, I would say you are the hardcore supporters of this webinar series. Thank you for staying on. Thank you for attending all the seminars, webinars. And if you have any questions, please contact us and we will try to see what we can do. We have shown you for every webinar different tools. So these tools are available. These tools can solve the problems. So hopefully people will start to use them. Okay, any questions? Then we will say thank you and goodbye. And we will see you for the webinar series 2022. Take care, stay safe. The COVID virus seems to be still there, so it has not gone. Okay, so bye-bye. So to the Thai team, thank you for all your good work. Now you can relax a little bit.
Okay, thank you.
Okay, bye. I'm going out.